Okay, we're going to look at heat pumps, and heat pumps can be thought of as sort of the reverse of a heat engine. Now, if we look at a heat engine and we graph the pressure as a function of the volume, we know to get work out that we want to expand the gas at a high temperature and compress the gas at a low temperature. Okay, and that is going to give us a net work that is positive because, again, when we expand the gas when it's hot, we get more work out of it than when we compress it when it's cold. We don't need to put as much work into it. So again, the net work done is going to be enclosed in this as long as we're going around this path in a clockwise direction. So heat engine, okay, is a clockwise direction on this path. We get work out. Now, if we reverse this cycle, let's say that we now, see if I can erase this, we now go the other way, and instead of expanding the gas when it's hot, we're going to compress the gas when it's hot. We're going to go from right to left, so that's negative work. Then we're going to expand the gas when it's cold and repeat the whole process over and over again. Now, if you think about a heat engine, we're getting work done out of it, okay? Heat pump is just the opposite, okay? Instead of getting work out, we're putting work into the system, and as a result, we are moving heat from the cold reservoir to the hot reservoir. So a heat engine, we go clockwise on these PV diagrams. For a heat pump, we go counterclockwise. Okay? All right. So let's take a look at some examples and see what is the same, what is different, and we'll also talk about coefficient of performance. So again, the heat pump, we're really imagining a heat engine running in reverse. Now, internal combustion engines don't easily run in reverse. Sometimes when we take our foot off the gas pedal when we're going downhill, we can use the compression to sort of absorb some of the work. So it's kind of acting as a heat pump. But heat pumps in themselves are their own specially designed devices. But again, we can imagine that instead of getting work out, we're putting work into the system. Instead of getting energy from the hot reservoir, we're taking energy from the cold reservoir and then transferring it to the hot reservoir. So, you think about a heat pump, and whereas a heat engine is sort of analogous to water flowing downhill and putting a water wheel there to extract work, a heat pump, we're actually, as the name implies, pumping the heat from a lower temperature to a higher temperature. And the most common examples of heat pumps are, of course, the refrigerator, freezer, the air conditioner, and of course, air conditioners that are specially designed to run both ways are oftentimes called heat pumps. So here's schematically what's going on. All right, we have some area we want to cool off. Okay, we'll call this the cold reservoir. All right, we'll call this a cold reservoir. It's at some temperature TC. Okay, we want to cool off a freezer, we want to cool off a refrigerator, maybe we want to cool off our own house. right? Its temperature is going to be colder than where we're going to dump the heat. We want to dump the heat to the outside. So let's say we want to keep our house cool. We're at 70 degrees Fahrenheit, but yet outside, it's a brutal 95 degrees Fahrenheit, okay? How are we able to get the heat out of the house and cool it down, where the second law of thermodynamics is going to say, yeah, you can't have heat naturally flowing from the cold reservoir to the hot reservoir? Well, we don't need to violate the second law of thermodynamics. We can add work to this system, and the addition of work is going to basically make up for the fact that the entropy, by putting heat from the cold reservoir to the hot reservoir, is going to decrease the entropy. The addition of work comes from the outside, where the entropy is actually increasing. Okay, so the water analogy is really good here. Okay, a heat engine, we're extracting work from the flow of water from a higher temperature to a lower temperature. A heat pump, just like a water pump can pump water uphill, we are pumping heat up to a higher temperature. Okay, now with heat engines, we rated them in terms of efficiency. Remember, heat engines, we said, well, the efficiency is how much work is needed, or how much work we get from the amount of energy input we put into that. And this had to be some number under 1. Okay. It's actually different for the heat pump, because the heat pump, we're simply moving energy, and we call the effectiveness of a heat pump the coefficient of performance. Okay, it measures how much heat we can move. In this case, if it's a freezer, if it's a refrigerator, that heat will be coming from the cold reservoir down here. So it'll be QC, how much QC we can move for the amount of work that we use. So it's not the same equation as efficiency, okay? And for most heat pumps, this is going to be quite a bit greater than 1. Maybe it'll be even as high as 4 or 5, depending on what the temperatures are. Generally, what we see is the greater the temperature difference between the hot reservoir and the temperature of the cold reservoir, okay, the coefficient of performance will go down. All right? There's not a lot of difference between the two temperatures. It's really easy to move the heat with very little work. But as we get colder and colder, the coefficient of performance drops. So if you look at your coefficient of performance on an air conditioner, that should be higher than what it would be on your refrigerator, right? Your air conditioner, again, you maybe want to cool your house down to 70. The outside temperature is 90. So there's a difference in temperature of 20 degrees Fahrenheit, not a whole lot. Your refrigerator is typically cooled down to 40 degrees, okay? A little drop in coefficient of performance there, and we're pumping the heat out to maybe 70 degrees in the house, all right? The freezer is kept at 0 degrees. So again, that coefficient of performance is going to be greater, is going to be less. So again, coefficient of performance can be thought of as sort of the ease at which it is to move the heat. And if you're moving it over not such a large temperature change, then the coefficient of performance is going to be quite high. And you're going to be able to move a tremendous amount of heat for very little work. Okay, refrigerant. Once again, what exactly is going on here? Well, we have heat that we want to remove from the inside, okay? And to do so, we are introducing work. And you can see there's a little plug right here that hooks up to a compressor motor. So that is going to do work on some refrigerant. And as we add work to this, it is going to leave out the backside, okay, as QH. And the same thing still holds. QH here is equal to QC plus W. This is conservation of energy, right? We are looking at removing some amount of heat, QC. So let's say in my refrigerator, I want to remove 1,000 joules of heat, okay? Now, let's say my coefficient of performance is 2. So I need 500 joules of work to do that. Well, what's going to come out the backside of the refrigerator? Well, conservation of energy says I need to exhaust 1,500 joules of heat on the backside. If you ever feel the backside of a refrigerator, or in some cases this might even be visible, there's a heat exchanger back there that gets hot. Here's the interesting thing. With a refrigerator, if you kept the door open, okay, left it in a room, the refrigerator would act like a heater. Why is that so? Because you'd be doing 500 joules of work. It'd be open to the outside, so there'd be constant heat flowing in. You'd be moving 1,000 joules in this particular case, and the room would end up with 1,500 more joules than it, I'm sorry, 500 more joules than it started out with. Yes, you would have moved 1,000 joules, but you'd just be moving the 1,000 joules from the inside of the refrigerator to the outside. And since they're both connected with the room gets 500 joules of heat. So the interesting thing is a refrigerator is made to keep the contents cool, okay? Again, you normally set this down to about 40 degrees Fahrenheit. But if you leave the door open, you're just adding electrical energy, which has become work, which has become heat, to the room. Freezers is even worse, okay? That coefficient of performance is much less. So, you know, much less efficiency there. Now, originally, how did we move this? We used to use chlorofluorocarbons, all right? They would be put in the refrigerant coils, the actual device that's going to cool this down. And CFCs, chlorofluorocarbons, were great because they had a nice moderate heat capacity to them, so they could absorb a lot of energy. They would change phase very easily at moderate pressures, so you didn't need a very fancy high pressure system. They just did the job very well, and they were a lot safer than ammonia refrigerators, which were actually the first ones, because the ammonia would react with things and could blow up. So CFCs were inert, and they were deemed to be safe. Soon we found out that the CFCs were destroying our ozone layer, so they were replaced with other fluorocarbons which didn't have chlorine in them, and that's the refrigerant that we use today. It's not as effective as the chlorofluorocarbons that were used, but it does a good enough job. So here is the inside of a refrigeration system, okay? This is something that you might find on a freezer. You might find something like this on a refrigerator. You might find it on an air conditioner. And you see a lot of copper piping here. And that's where the refrigerant is going to flow through. So basically, there are two heat exchangers that we typically have. There's one heat exchanger which is going to absorb QC, and there's another heat exchanger. Usually we use a fan to blow out QH, and that's going to dump it into the surrounding areas. What I don't see here is I don't see, oh, maybe this is the compressor pump. I'm not sure. But somewhere there's a compressor pump which is going to pump the refrigerant and is going to actually introduce the work. On this particular diagram, should have used a diagram where the compressor pump was obvious. That looks like it might be a compressor pump on the bottom. Compressor pump might be someplace else, but that'll add work to the system. Okay, how does it work? How do we get the heat to go from the cold reservoir into the hot reservoir? Okay, I want to get QC into the refrigerant, and I want to dump the excess heat out into the environment. Okay, actually, it's being dumped into the hot reservoir, and we're absorbing the heat from the cold reservoir. Okay, so how am I going to get this to happen? All right, I'll use the refrigerator as an example, because that's usually a pretty good application. Again, this will work well for an air conditioner. This will work well for a freezer. The freezer, again, the coefficient of performance is going to be less, so it's going to have to work harder. The air conditioner, probably not as hard. Okay, so and I apologize for using US customary units, but we're going to use US customary units because it's just easier for most people to figure out what's going on. Okay, so the temperature inside my refrigerator, I want to keep at 40 degrees because that's going to keep my food fresh. Let's say that we're dumping heat to the outside and the room temperature is 70 degrees Fahrenheit. Okay, now heat is not naturally going to flow from the cold reservoir to the hot reservoir. In fact, if I leave the door open, it's going to get warm in there as heat goes from the outside to the cold reservoir. So again, our hot reservoir is the room. Our cold reservoir, in this case, is the refrigerator. Okay, how am I going to do this? All right. Well, the refrigerant is going to be colder than the refrigerator. Okay, the refrigerant that I'm using, whatever it's made out of, okay, it is going to be colder, and I'll explain why it's colder in a little bit, but it's going to be colder than the temperature of the refrigerator. Okay, maybe it's cooled down to, we don't want frost to appear, but let's say the refrigerant is cooled down to about 30 degrees Fahrenheit. Okay. It depends on the refrigerator. If there's a separate loop for the freezer and the refrigerator, but obviously, if the refrigerant is colder than the inside of the refrigerator, it's going to absorb heat. Okay. Now, here's where the work is done. My compression pump, my compressor, as they call it, is hooked up to the electrical grid. There's a little electric motor that is going to turn this pump, and it's going to adiabatically compress the refrigerant. Okay, remember adiabatic compression. This is like the Santa Ana winds. We go from a lower pressure, lower temperature, we do work on the system, and suddenly the refrigerant becomes much hotter. Okay, so now let's say I've compressed it so much that the new temperature is like 120 degrees. Okay, it's going to be hot. Feel the back of your refrigerator sometime, it gets hot. So even though outside, which is the room, is warmer than the inside of the refrigerator, the refrigerant is going to give up its heat to the room. It's going to be the QH, okay, because heat naturally flows from 120 degrees to 70 degrees. Okay, so now the refrigerant comes back around and it goes through an expansion valve right here, okay? Now, you need to do work on a gas to compress it. That's why the compressor pump is on the left-hand side of this diagram, okay? Again, over here, we have adiabatic compression. Compression takes work, and that's why we need to have the pump on that side. But on the other side, we don't need anything. We have adiabatic expansion. Okay, it's just going to expand, and as it does so, it's going to cool down to its lower temperature. Okay, so it'll go back down and it'll be cold again. And of course, if this were a freezer, the temperature of the refrigerant would be even colder. Maybe the temperature of the refrigerant would be like negative 20 degrees Fahrenheit. And that would allow the inside of the freezer to drop to a much lower temperature. But, you can see how this works by using adiabatic processes to compress the gas to heat it, the refrigerant to heat it, and to expand the refrigerant to cool it. We can move the heat fairly easily, okay? And again, on both sides, you have a heat exchanger within the place you're trying to cool down, and you have a heat exchanger where you're actually dumping the excess heat. So again, coefficient of performance for these systems are rated by how much heat we remove from the inside of the cold reservoir divided by the amount of work that is done. And usually the higher the number, the better. Because a refrigerator won't move across a very large temperature gradient, you can get a coefficient of performance of 5 or 6. And if you look at this, that basically means that to move 1,000 joules of heat from the inside, it's only going to take between 167 joules to about 200 joules of work, okay? So you can actually move much more heat than the actual work that you need, okay? Anytime you have a coefficient of performance greater than 1, you're moving more heat than the amount of energy required. But you have to remember here, this is still conserving energy. Work is going in here, okay? And QC is going in here, and then they both add together to produce a net outward of QH, where QH is equal to QC plus W, okay? Better coefficient of performance, more efficient, better refrigerator. And again, for a freezer, it's going to be much lower than a 5 or a 6, because you're trying to cool down to about 0 degrees Fahrenheit. You can also use a heat pump to heat your house. Now, it's not in the heat engine. It's not like we're reversing it. We're just switching what is the cold reservoir and what is the hot reservoir, okay? Now, for the heating mode of a heat pump, we talk about the coefficient of performance is how much heat we dump into the home compared to how much work is done. All right? All right, think about your house. When it's summertime, you want to move the heat outward, okay? So you're dumping QH outside of the home. When you are wanting to heat the house, you are bringing in heat from the outside or the ground. Okay, here's something that's very important. Traditional air conditioners and heat pumps that simply exchange energy with the outside air, very inefficient. And here's why. When we exchange with the outside air, we're normally doing it over a larger temperature gradient, okay? This heat pump, you'll see, is actually using pipes in the ground. Why pipes in the ground? Because the ground stays around 50 degrees Fahrenheit, okay? Think about it this way. If I'm dumping heat in the summertime at 50 degrees Fahrenheit, well, that's easy. If my house is 70 degrees Fahrenheit, okay, it's going to want to naturally go here. So the coefficient of performance is going to be really, really high as long as I'm dumping it into the ground. Now, if it's 90 degrees outside, I'm having to push the heat to a higher temperature. So an air conditioner that simply exchanges with the air is much less efficient than a geothermal heat pump. And when they're talking about geothermal, they're basically saying they're exchanging heat with the ground. Okay, let's look at the heat pump in heating mode. Okay, we're going to get rid of this. We're going to get rid of this. We're going to get rid of this. All right. In heating mode, you want to move the heat from the outside to the inside. Okay, so let's say that it's 20 degrees Fahrenheit outside, cold outside. Okay, you could extract heat from that 20 degrees Fahrenheit, but it's going to be really, really difficult because you're moving up against a 50-degree heating gradient. Okay, you're going from 20 to 70. And when it's 0 degrees outside, the heating grade, the temperature gradient is even larger. But if you're getting the heat from the ground, which naturally all year round stays 50 degrees, then you only have to increase your temperature by 20 degrees Fahrenheit. Okay, so geothermal heat pumps are very, very efficient, much more efficient than standard air conditioners and standard air heat exchanger heat pump type systems. The problem with them is they're very expensive to bury all this pipe underground. Okay, it used to be that they dig up an entire field and they lay all this pipe and snake it back and forth. Now they do it mainly with vertical drilling. Okay, but it still costs a lot of money to install. So again, geothermal heat pumps, basically in the summertime, you're extracting heat energy from the ground, okay? And the ground has a lot of thermal capacity. You're not going to cool the ground off very much, but you're taking this heat and you're dumping it inside. Oh, I'm sorry, other way around. I had my seasons reversed. In the summer, you want to cool the building, so you want to dump the heat into the ground. Okay? In the wintertime, you want to do the reverse. You want to extract the heat from the ground. The ground, if you dig deep enough again at 50 degrees Fahrenheit, has a tremendous amount of heat energy. You can just use that to heat your building. Okay? And here are different coefficient of performances, which tells you how effective they are. Here's a through-the-wall air-cooled air conditioner. Okay, less than 30,000 BTUs. That's not a bad coefficient of performance. However, that would be when it's not all that warm outside. That would sort of be the maximum coefficient performance. And then you can see some water-cooled air conditioners have a higher coefficient of performance because they use the evaporation of water to actually enhance them. All right. And here is a coefficient of performance for an air exchanged heat pump. This is, using commas instead of decimals. So you can see when it's negative 15 degrees centigrade outside, Celsius outside, coefficient of performance is only 2.6. As it gets warmer outside, coefficient of performance goes up. And again, thinking about the temperature of the ground is usually at a constant 50 degrees or about 15 degrees Celsius. So, a coefficient of performance for most heat pumps would be about 4.5.